when we have a problem like this, three single phase loads, they're on a 400 volt 3-phase 4 wire, so I've got a neutral, determine through phasor addition the value and direction of the current in the neutral conductor. So there's our loads for each phase. On the A phase we've got a 10 amp 0.9 leading power factor, so the angle for that would be inverse cos 0.9 gives us an angle of 25.8 degrees. So we can make a note of that now. For our phasor construction will be 25.8 degrees. The angle whose power factor is 0.65 is inverse cos 0.65, and that's 49.5 degrees. 49.5 degrees. And of course we've got a purely resistive element in the C phase, a 3.6 kilowatt kiln. It's the current phasor we're developing, so the current drawn, the power divided by the voltage, 3600 watts divided by 230 is 15.7 amps as the current, and of course that'll be in phase with the voltage being purely resistive. So construct your phasor, come up with some scales of course, so we'll do the voltage where 1 centimetre is equal to 28.75 volts, so we can construct our voltage references. So VA is 230 volts, VB 120 degrees later, considering our direction of rotation of the phasor is in anti-clockwise direction, so round at 120, another 230 volts for B phase. VB 230 volts, and the C phase another 120 degrees up there. So there's our voltage reference phasor. We can plot the currents onto it. Okay, so VC also at 230 volt potential. 10 amps on a 25.8 leading power factor. So there's our horizontal reference for the phasor in an anti-clockwise rotation. So if the current is leading, it's going to be up in this sector of in reference to your A phase voltage. So it's leading by 25.8 degrees. So we'll plot that one in. 25.8, it's just above there, and it's 10 amps long, so we'll come up with a scale, say for current, where 1 centimetre can be equal to, let's say, 2 amps. So that's going to be 5 centimetres. We'll plot that up there, so that'll be, what did I say, 5 centimetres long. And that's IA, which is 10 amps, and that's leading by that, there's that 25.8 degrees in there, leading the reference. The B phase is a 15 amps lagging power factor, which we worked out was 49.5 degrees lagging, so it's going to come after the B phase out here at 49.5 degrees after the B phase. So we reference that B phase and come round at 49.5, 49, almost 50 out to there, and that's 15 amps, 2 amps per centimetre. That'll be 7.5 centimetres long, representing 15 amps. Okay, so that's our IB at 15 amps. And the IC value purely resistive, so it's in phase with the voltage at 15.7. So that'll be, how long will that? That'll be 7.85, 7.9 centimeters long. Oh, sorry, and purely resistive, 7.9, which is about there. Okay. So there's our three currents. IC at 15.7 amps. So phasor addition will determine the value of neutral current then. So again, doesn't matter which phases you select first. So I'll add IB, add to IC, and we've gone off the page. So that's just a big stuff up. Alright, what about if we go this way? Might stay on the page. So we go from there to the tip of that, scribe an arc. Get the length of this one. Turn it around, go to the tip of this one, scribe an arc. Where those two arcs intersect gives us a resultant of IC plus IA. That value down there. And we can add that now, that resultant, to IB. Okay, so again, we'll get the length of IB, come to the tip of that resultant, scribe an arc, and get the length of that resultant, and come down to IB and scribe an arc. And where so they've added the three phases, and where those arcs intersect will be the value of neutral current in the circuit from there back to the start point in there. So if we go there with that, there's the final result, IN. Up to there, which is IN. And that's equal to, let's say 10 centimeters long, which is equal to 20 amps is the value of neutral current in that unbalanced load system. The direction of neutral current is always flowing towards the start point, whereas the phase currents are flowing away from the start point.